Hi, my name is Ray Poynter from the Future Place, and I'm going to try to give you in 15 minutes an introduction to hierarchical Bayes. So, I think we need to ask, why do we need hierarchical Bayes, or HB to its friends? The traditional view of solving equations was like this. So here's a very simple linear equation, y equals mx plus c. So we're trying to solve it for x. What have we got? We've got one unknown, so we would need two observations to be able to fit that. And it's a straight line. If we've got 2 points on the chart, we can join the straight line together. If we wanted to solve a quadratic, something like y equals ax squared plus bx plus c, to take you back to high school, we've got two unknowns. We've got the x and the x squared effectively. So we're going to need 3 observations. If we've got 3 points on our graph paper, we can actually plot that quadratic. There's only one quadratic going to go through those 3 points. More in a market research situation, we've got here y equals beta 0 plus beta 1 x1 plus beta 2 x2. So we've got 2 x's. They've both got their own arguments. We want to solve them. We need 3 observations. So it's an absolute pattern that we see. If you've got n unknowns in the data, then the minimum you require to estimate those is n plus 1. What about HB? Well, if you've done any maths, you might be familiar with this symbol, which is approximately equal to. And for some people, HB is approximately equal to magic. And why is that? Well, it deals with things like 40 unknowns and 12 observations, yet it'll have a bash at solving that, which seems quite outrageous. We've got more unknowns than observations, and it's going to have a go at solving it. So how does it do that? Well, imagine that I was to introduce you to a taxi company, and I'm going to tell you that a company has 3 drivers, Andy, Bob, and Chris, and I tell you one of them has had a crash today. If you had to guess who, you'd have a 1 in 3 chance. That's how you'd think about it. But if I say Andy and Bob have never had a crash in all the years they've been working for me, and Chris has had 15 crashes already this year, you might start to think that Chris was the person most likely to have had today's crash. And that's an example of Bayesian thinking. It's also an example that was first shown to me by Rich Johnson at Sawtooth, so I thank him for that. And what we're doing is we're carrying prior information in. And it turns out that the brain does this all the time. Every time we see a new situation, we try to carry prior information into it. And this, in a formal statistical sense, dates back to the Reverend Thomas Bayes back in the 18th century. So he's not exactly an overnight success. And what he produced, for those of you who can remember their stats in high school, is the probability of x given y is given by this formula here, the Bayes theorem, which is the probability of y given x multiplied by the probability of x, all divided by the probability of y. Way too complicated to run through in our 15 minutes. So we can make it much clearer with an example based on a nasty disease called Bayesitis, which is fortunately very rare. Only 1 in 1,000 people have it. So let's have a look at that example. 1 in 1,000 people have Bayesitis, so the chance is just 0.1%. The test is very reliable. If you have Bayesitis, the test will be positive in 99% of cases. If you don't have Bayesitis, the chance of a negative result is 95%. So there are not many false positives, there are not many false negatives. Consider, you are tested and you get a positive result. What is the chance that you have the disease? So I want you to write this down on a piece of paper for me, and I will look over your shoulder in a moment. If you've got the disease, then there's a 99% chance but the test will tell you it. If you don't have it, there's a 95% chance it will tell you don't have it. You go for the test, it tells you that you've got the disease. What's the chance you've really got it? I wonder how many of you have written down numbers over 50, maybe even over 90. The answer is it's just under 2%. We can illustrate that with this very simple way of looking at it. Imagine we've got a population of 1 million people. The probability of having the disease, 0.1%. So amongst our 1,000,000 people, 1,000 of them should have the disease, and 999,000 should not have the disease. Amongst those 1,000 people who've got the disease, we know that 99% of them should get a positive result. So 990 people get a positive test result, and 10 of them, unluckily, are told that they don't have Bayesitis, even though they do. We take the 999,000, we know that just 5% of them will get a positive result, even though they do not have it. It's right 95% of the time, it's wrong 5% of the time. So of these people, 49,500 of them get told that they've got a positive result. So if we add together the two groups of people who got a positive result, the 990 and the 49,500, we get 50,490. 990 of those people are real, which is 1.96 of all the results. That sort of thinking, the Bayes theorem way of thinking, shows why so often conventional stats produces a problem. But what about hierarchical Bayes? And in the context of choice data, what happens in choice data is that we have a two-level model. That's where the hierarchical bit comes into it. In the upper level, we have the part worth for a respondent, and we assume that for every person, their part worths are part of a multivariate normal distribution. If we add all the people in, we'd all have a distribution, and above that is a bigger distribution. In the lower level of the model, we have the logit assumption that the probability of choosing X is the transformed utility divided by the sum of all the transformed utilities. So we have the conventional part of a conjoint analysis going on within that. The computer then uses Markov chains, Monte Carlo simulations. It generates random numbers in a particular way, incredibly computer intensive. And what it does is it forms a forecast of what the individual level results would have been from the choice data, even with many parameters and relatively few choices. Why do we do that? Well, in choice-based conjoint, we often have too many tasks. If we were to really ask respondents to do it, they'd have to do 100 computer screens or 50 computer screens of tasks. We can't, because people won't do it and their brain hurts if they try to do it. So we have lots of variables and not enough observations. So that's why we use hierarchical Bayes. Does it work? Well, this chart here is from John Pennell. If you get the chance to hear John talk on a range of advanced techniques, I strongly suggest it. He's based in Cincinnati, very knowledgeable guy. Here's a study he did back in 2000. First study, aggregate logit, which is what you have to do if you don't have hierarchical Bayes. All you have to do is just make an overall model. And they found that the hit rates went up from 75.8 to 99.5. A really good improvement. Study 2 was really a very poor study, which suggests that there's heterogeneity in the data. It went up from about 25 to 80%-ish. Study 3, modest improvement. Study 4 showed a nice big improvement from 61% up to about 79%. Study 5, good improvement, 59% up to 79%. So we see these big increases in hit rates, which makes us feel very happy about hierarchical Bayes. However, John did produce one study where it was slightly worse after hierarchical Bayes. He noticed that that was a partial profile study and has gone on to produce some other results that show hierarchical Bayes works really quite badly with partial profiles, cases where you don't show all the attributes. It looks like there just aren't enough patterns in the data for it to be able to make those estimates. So why did we need hierarchical Bayes? It allows us to estimate individual utilities for discrete choice modeling, which with discrete choice modeling was the missing piece. When we went from old-fashioned conjoint studies to discrete choice modeling, we started having to use aggregate models, build a model of all the regular users and the irregular users, or the men and the women, or just a total model for the sample, because we weren't asking enough questions to each person. With HB, we go back to the thing that we really want, which is an individual level model. Hierarchical Bayes also opens up other cases where sparsity of data meant individual results not available. So it's very often used in MaxDiff to avoid people having to do masses and masses of max diff. It can be used in bundled choice modeling scenarios, again, to reduce the number of questions that are asked to each person. So hierarchical Bayes is very, very useful in that it reduces the number of questions we ask to each respondent without us having to give up on the amount of information we get at the end of the day. And here is an incredibly simplified idea of how it does that. Each person within the study gives us enough data to build up a bit of a picture, but none of those pictures explains their behavior. It doesn't tell us about their utilities. In aggregate, we can do that. We can bring all the people's data together and we can form an aggregate model, but it doesn't tell us about the individuals either. So what we can do is use hierarchical Bayes computing power and time, and it starts generating lots and lots of possible universes. Could the world look like this? Might the world look like that? And each time it generates one of those, it compares it back and says, could those people really have come from this universe? The more likely it is that those people could have come from this universe, the higher the weighting for that universe. At the end of the process, we can send data back to each of those individuals from the combination of universes that seems most plausible and end up with a complete set of data for each one of those respondents. So what was the impact of hierarchical Bayes on this choice data? Well, if as a respondent you were quite typical of the database, actually HB changed your results very little. But what we did find is that if you're an outlier, it tended to squeeze you back towards the mean. Now that makes the data that comes out of hierarchical Bayes more consistent, but it does mean that it's not going to be as representative of you as an individual. Data from groups of people who've been through hierarchical Bayes, through the hierarchical Bayes machine, if you like, are normally good predictors of how the group should behave, but they're not necessarily good predictors of individual levels of data. If you take the raw data that you collected and you look at the predicted choices within that, it won't always predict what people actually said at the individual level. It's really good when you group the data together, but it doesn't actually recreate those individuals. And we need to bear that in mind when we're using the data. HB is very useful. It will allow us to do disaggregated modeling. It will allow us to post hoc group the data, but it's not magic. We still have a fundamental problem when we have more unknowns than we have observations. So whilst it's incredibly useful, we mustn't run away with the idea that it's actually recreated accurate representations of each individual. So I hope that's been of some advantage to you, and I look forward to your questions.